What we have seen in the last class was mapping of complex function, how to plot the image of points, curves and regions under a complex map. And we have seen to plot a complex map we need two planes. One we call as the z plane where we plot the values of z, and the other we call the w plane where we plot the values of w equal to f of z. Now today we are going to see the concept of conformal mapping, and before entering into that topic, let us discuss about some important points while we consider a complex mapping. And those points are fixed points, zeros, regular points, singular points and critical points. So when you come to fixed points of complex map w equal to f of z, those are points for which the map is that point itself. For example, if f of 2 plus 3i happens to be 2 plus 3i, you can say that 2 plus 3i is a fixed point. If f of 2 is equal to 2 itself, then 2 is a fixed point. So in general, we say that z is a fixed point of w equal to f of z if f of z equal to z itself. If a point is mapped into itself, then that point is called a fixed point. Now zeros of the function w equal to f of z. So zeros are the set of all points z which is mapped to the zero of w plane. So the collection of all points whose image is 0 is called the zeros of the function f of z. Or formally we write z is the 0 of f of z if f of z is equal to 0. Now regular points are points where the function is differentiable. So if z is a regular point, that means f dash z exists. And singular points are the opposite of regular points. That is, at a singular point, f dash z will not exist. So the set of all points at which f dash z doesn't exist is called singular points. Now, when you come to the critical points, those are zeros of the derivative function. So critical points of a function are the set of all points at which the derivative is 0, f dash z equal to 0. For example, let us consider the function f of z equal to z square minus z. So if you consider this function, let us find the particular points we discussed now for this function f of z. So the first thing we have seen is fixed point. So for fixed point, f of z is equal to z itself. So here the map is given to be z square minus z. So z square minus z should be equal to z. So in other words, z square minus 2z should be equal to 0. Or taking z as common, we can write z into z minus 2 equal to 0. Or z is equal to 0 or z is equal to 2. So when you look at this function, if you directly substitute for z, you can see f of 0 is equal to 0. That is, the image of the point 0 is equal to 0 itself. So 0 is a fixed point. F of 2 if you find, that is equal to 4 minus 2 equal to 2 itself. So 2 is a fixed point. So while you do it like this analytically, you get the set of all points. So here you can say that z is equal to 0 and z is equal to 2 are the only fixed points of the function z square minus z. Now if you want to find the zeros of this function, so zeros it is the collection of all points where f of z is equal to 0. So f of z is z square minus z. So z square minus z will be 0. Again, taking z as common, z into z minus 1 equal to 0. That is, z is equal to 0 or z is equal to 1. Hence, the zeros of this function are 0 and 1. This means that f of 0 will be equal to 0 f of 1 will be equal to 0, and 0 and 1 are the only points satisfying this. The 0 and 1 are the only points whose image is 0. So you can see this by substituting the value 0 and 1 here. You will get 0 minus 0 equal to 0, 1 minus 1 equal to 0. Now the next thing we have seen is the regular points. So regular points are points at which the function is analytic or differentiable. And we know this function, we have seen that all polynomials are differentiable functions. So this is a polynomial of degree 2, hence this is a differentiable function. And we know f dash z is equal to 2z minus 1. The derivative exists at all points. So f dash z exists for all z, right? There is no peculiarity for z. For any complex number, this 2z minus 1 is the derivative of the given function. Or in other words, all points are regular points. So when you speak of singular points, I mentioned that singular points are opposite of regular points. That is, a point which is not regular is called singular. So if all points are regular, it means that there is no singular point. All complex numbers are regular points, or all points z are regular, hence there is no singular point. Now come to critical point. So critical points are points at which the derivative is 0. So f dash z equal to 0. And f dash z is 2z minus 1. So 2z minus 1 should be 0, or z should be equal to 1 by 2. So the critical points of this particular map is z is equal to 1 by 2. Only one critical point. And singular points and critical points you will see again while discussing conformal mapping. We need the concept of critical points, and while doing complex integration, the main thing we look for is the singular points of a function. So remember, singular points are points where the function is not analytic. Now let us see the definition of an analytic function. So a function is said to be conformal at a point if it is angle preserving at that point. So suppose w equal to f of z is a function, and suppose that z0 is a point in the z plane. Z0 is a point in z plane, and C1 and C2 are two curves that passes through Z0. So obviously they intersect at Z0. So we measure the angle of intersection from C1 to C2. So this direction of measurement is also important while you consider conformal mapping. So we find the angle of intersection, that is angle between the tangents at Z0 from C1 to C2, and let that angle be alpha. So we have the map W equal to f of z. So under the map f of z, C1 will have an image C1 star, and the image of C2 is C2 star. Now Z0 being a point on C1, f of Z0 will be a point on the image of Z1. Similarly, it is a point on the image of C2. So as it is a point common to C1 star and C2 star, we can say C1 star and C2 star intersect at f of Z0. Now suppose the angle measured from C1 star to C2 star is alpha itself, then you can say that the map is conformal. So the C1 and C2 are any two curves intersecting at Z0. So for conformality, it should be true that for any curves, not only for a pair of curves C1 and C2, For any curve that passes through Z0, the angle of intersection should be preserved in magnitude and direction under the map. And in magnitude and direction, we mean that, see, suppose C2 star appears here and C1 star appears here. That is, these images are flipped. Then, if you measure the angle alpha, it will be from C2 star to C1 star. So, if you measure the angle from C1 star to C2 star, if they are flipped, the angle will be minus alpha. So, that means the value, the magnitude is preserved, but the direction is not preserved. So, in that case, the map is not conformal. We say that it is an isogonal map. So, for conformality, the direction is also important. If you are measuring from Z1 to C2 in the image plane W plane, you should measure the angle from C1 to C2 itself, and you should get it as alpha itself. And this should be true for any pair of curves that passes through Z0. Then we say that the map is conformal. Now, so conformality is a property of the map W equal to f of z, as well as a property of the point Z0. By saying so, I mean that if f of z is conformal at Z0, it doesn't mean that f of z is conformal everywhere. It may not be conformal at a different point Z1. Similarly, if f of z is conformal at Z0, doesn't mean that every function is conformal at Z0. Some g of z may not be conformal at Z0. So, conformality is property of that function as well as that point. So, when you consider the conformality, we have some conditions satisfying which you can conclude that map is conformal. And when you consider that the condition for conformality is, suppose W equal to f of z is conformal at, it should be Z0. Z0, if the angle between curves through Z0 is the same as the angle between their images f of Z0, both in magnitude and direction. And the condition for conformality is this: if the map W equal to f of z is analytic and f dash z not equal to 0. If f of z is analytic and f dash z not equal to 0, then f of z will be conformal at z. Or in other words, if f of z is analytic at z0 and f dash of z0 not equal to 0, then f of z is conformal at z0. So, analytic function, once you have an analytic function, you look for the critical points. Critical points are points at which f dash z is 0. At critical points, the function will not be conformal and it will be conformal at every point except at critical points. So, that is the importance of critical points. At critical points, the function may not be angle preserving. But if the function is analytic, it is conformal at all points except the critical points. So, we can say, if you consider this function, f of z is equal to z square minus z. We have seen this is analytic at all points. It is differentiable everywhere. And the critical point is z is equal to 1 by 2. So, you can say that this map will be conformal at all points except z is equal to 1 by 2. Okay, we will see some more in your syllabus. Some special maps are included like e raised to z sin z 1 by z, etc. And we will see those maps in the next class.